Okay, so this video is going to be talking about answering the post-lab questions that for the titration curve lab. That is the last lab we finished before this whole thing happened. So we're just going to go through how to do some of those calculations. Looking at the post-lab questions, the first question is what is the concentration of the phosphoric acid solution? We're going to show any relevant calculation. So the first thing we need to show is our titration curve. That's the data you should have collected. Your lab partner should have it. You can use my template I put on Moodle to plot that data out, and so you'll be able to use it. I'm just going to draw what it should look like, and using some of the data I've gotten from some students. Thank you very much to those students who sent me that data. I can kind of approximate things, but I'm just going to draw a quick little titration curve here where it should, of course, it's going to be difficult. Titration curve should look something like this, where you have pH on the y-axis and the volume of the sodium hydroxide solution on the x-axis, and that should be in milliliters. You should know that concentration. You should have written that down. I gave that to you during the lab as I standardized that and gave you that value, so you should have that. Let's just quickly put some axes labels here, and again, Excel will do all this for you. And of course, I didn't make it tall enough. So let's just extend this a little bit. Okay. So the pH should have started off somewhere around 2 or 2.5, and that was with 0 of the NaOH added. And as we added NaOH, the pH should have gone up. Not very much. What we're going to learn in the next chapter is that this is called the buffer region. Somewhere around 4, 4.5, 5, the pH should have changed rapidly and then began to level off again, and then kind of entered this buffer region again where the pH isn't changing very much. And then somewhere around 9 or 10, it should have increased rapidly again, and then finally leveled off somewhere around 12, maybe a little bit above 12. So we can see here we have 2 points where the pH was changing rapidly. And as we've learned from our lab packet, that's called the equivalence point. So somewhere right in the middle there, I'm just estimating, I'm going to call that the equivalence point. So question number 1 asks, what is the concentration of the H3PO4 solution? So we need to remember concentration, molarity, is simply the moles of H3PO4 over the liters of the solution. We'll tackle the easy part first. The liters of the solution is just how much of that phosphoric acid unknown did you put in the beaker. So I can leave you to check your lab procedure for that. So that is how much unknown solution. It's written in the procedure. You just need to go back and remind yourself what you did. So the next part of this, we've got the liters, or you can look that up really quickly. The next part of this is we need to get the moles of H3PO4. So we're going to use the volume of the base that we added and the concentration in order to get that value. So the first thing I want to label here is the equivalence volume. So that's the volume it takes. So this was at 0, and this is some volume later, x. I'll leave that for you to analyze your own data and kind of come up with your own numbers. So from 0 to x is our equivalence volume. That's the number of milliliters it takes for the reaction to reach its first endpoint. The reaction, we should always remember what the reaction is. H3PO4 plus OH is forming, and it's definitely not an equilibrium. OH is a strong acid. This is going to go to essentially to completion, where we get H2PO4 minus and H2O. So we're converting, using the strong base hydroxide, we're converting all of the phosphoric acid into the dihydrogen phosphate. So that's where we're going to get the number of moles, because at this equivalence point here, the moles of the phosphoric acid is equal to the moles of the hydroxide. So we're going to come down here and we're just going to say question 1, the work for question 1. The moles of the H3PO4, try not to be sloppy here. H3PO4 is going to come from the equivalence volume. So I'll leave you to get the equivalence volume and fill in your own data there. That's in milliliters, so first thing we need to do is convert from milliliters to liters. So we say 1,000 milliliters for 1 liter. And then this is where we use the concentration of the hydroxide. So you should have that number. It's the number of moles of hydroxide. So whatever molarity you wrote down, you're just going to plug that number in there over the liters. And so we say 1 liter of hydroxide. Even though we may not have used 1 liter, we're taking care of that by multiplying by the equivalence volume anyway. So now we have an answer that is, if we go back and double check here, we're crossing things out. Now we have an answer that is the number of moles of hydroxide. So we just need to convert from moles of hydroxide to moles of phosphoric acid using our balanced balanced equation, I should say. We say for every 1 mole of the NaOH, we use 1 mole of the H3PO4. So it's just 1 to 1. We get the same number. So you should get some number of moles of the H3PO4. So to get the molarity, you just take that number of moles, back up to our top equation up here, and plug that number in right there at the top. And then you plug in the volume that you get, and you simply divide the number of moles by the liters of solution that you use. Make sure you convert that number into liters, and you should get the concentration of the phosphoric acid. It should be somewhere between, I'll just give you a little hint here, it is somewhere between 0.5 and 1. So it's greater than 0.5 but less than 1 molar. It gives you a little guideline of your volume or your concentration you should be getting. All right. What you can also do, and this is still question 1, part 2 I guess, is that you can use the second equivalence volume to do the same thing and kind of double check to make sure that it's all working out. Now if I had drawn this properly, these 2 equivalence volumes would be the same. One's a little bit bigger than the other, but again, using your own data, you can get the second equivalence volume. And the reaction for that is the H2PO4 from the first reaction plus the second equivalence volume of hydroxide is going to form HPO4 2- and another mole of water. And what you can do is you can use this second equivalence volume and plug that into the same equation. So you're going to repeat with second equivalence volume. And you should get roughly the same number of moles. You should get roughly the same concentration because all of the moles in the second reaction came from the first reaction. So these 2 should be equal. The concentration should be equal. It really is going to vary depending on where you pick your equivalence point to be in these 2 steps. All right. Question 2, what's the molarity of the phosphoric acid and hydrochloric acid in the mixture? We didn't do this step, so you don't have to do this problem. Look at that, look how easy that was. Part 3, what are the values of Ka1 and Ka2? To do this, we're going to need to use an equation we haven't quite talked about in lecture yet. I'll be posting a lecture about that fairly soon here when we get to this chapter. It's the next chapter. We have this equation called the Henderson-Hasselbalch. I introduced this during lab. We say the pH is equal to the pKa plus the log of the ratio of the concentration of the weak acid over its, the weak conjugate weak base over its weak acid. So we have A- over HA. What happens is that at the half equivalence volume, or the half equivalence point, the concentrations of A- is equal to the concentration of HA. So this is to say at halfway in this reaction, so let's just draw this up right here. Halfway into this reaction, we've converted half of the H3PO4 into H2PO4. So we would essentially have 0.5 over 0.5. If we started with 1 molar, it would be 0.5 over 0.5 in this Henderson-Hasselbalch equation. So since these 2 are equal to each other, that means this log term becomes the log of 1, since anything over the same thing as 1, and the log of 1 is equal to 0. So at the half equivalence point, this thing happens where the pH is equal to the pKa. So now we already know how to get pKa into Ka. We just have to take 10 and raise that to the negative power of that number. So we just have to look at our data and find out what is the pH at the half equivalence point. And we're going to come over here and estimate. I'm going to say, yeah, it looks like it's right about 3. So we'll say the pH is 3 at the half equivalence point. And we know that the pH is equal to the pKa. So now our pKa is 3. Well, to get the pKa into the Ka is just 10 to the negative pKa gives us the Ka. And if we crunch that number really quickly, we should get 1 times 10, at least the number I got with my estimation. Again, you want to do this with your own data. I get 1 times 10 to the negative third, which is in the same ballpark as the actual literature value of the Ka. So not bad on the estimation part. Again, you want to use your own data to see what you actually get. And the same process is true for the second Ka value. So this would be Ka1. Should be specific here. We're talking about Ka1. To get Ka2, we just need to go to the second equivalence point. So this is the second equivalence point. We need to take the half equivalence volume from there. So that's halfway between the first equivalence point and the second equivalence point. That looks like it would occur right there. And we just need the pH at that point. And let's just say it's somewhere around 8. So it's the same process. pH is equal to 8, so the pKa is equal to 8. And again, you just take the 10 to the negative 8, which give you the Ka, which again, just kind of crunching the numbers on this example, is just 1 times 10 to the negative 8th, which again is in the same ballpark as the literature value, so not bad on the estimation part. But again, you want to use your own data for this to actually get the correct values. So that's how we get Ka1 and Ka2. Question 4 is asking you to find the percent error between the Ka values you just got and the literature values. So I'll just give you the percent error formula. Percent error is given by the absolute value of the literature value minus the experimental value so these are absolute value bars divided by the literature value times 100. That's your percent error calculation. It's basically saying how far away were you from the actual value. So how far away was your experimental value from the literature value divided by the literature value. So it kind of scales it to the size of the literature value. And then you multiply by 100 to get the percent error. So you should calculate a percent error for Ka1 and 2. Finally, question 5. Let's go over here and answer question 5. Question 5 says, considering the literature value of Ka3, why were you unable to determine the value of Ka3 from your experiment? Simply stating that Ka3 is too small will not earn full credit. You must explain your answer using relevant chemical principles. So again, Ka3 is really small. It is 4.8 times 10 to the negative 13, but we can't just leave it at that. We actually have to talk about what that means. We know Ka3 from this experiment is talking about the dissociation of the HPO4 2- into its final product PO4 3- and a H3O+. So you can look back up on the couple pages on the lab manual. That literature value of Ka3 comes with that dissociation reaction. And let's just write this just for clarity here. HPO4 2- plus the water will dissociate into PO4 3- and H3O+. So our products and our reactants are concentration, the reactant is HPO4 2 minus, and on top of that is the PO4 3 minus and H3O plus. If we do a quick calculation with the ice table, we'd see the H3O plus based on the Ka value of 4.8 times 10 to the negative 13, concentration of H3O plus would be somewhere around 1 times 10 to the negative 7th, which is about the same as the autoionization of water. So the problem with this one is that the reason we can't see it is that it's comparable to the autoionization of water, and the pH probe just simply can't see that difference. It can't tell the difference between that and water. So the pH probe just says that there's no change, or that it's just so small the pH probe can't really actually distinguish it. So yes, I'm saying that Ka3 is very, very small, but the reason that the pH probe can't see that is that it can't distinguish it away from the water. And so essentially you're just adding hydroxide, and that's why at the very end of this titration the pH doesn't change very much. We've consumed all of the acid and you're just adding hydroxide to the solution, and after a certain point the pH probe becomes insensitive, and it looks like between 12 and 14 the pH probe just can't really see a change anymore, and that has to do more with how the pH probe works, not having to do with any differences in the actual reaction. So hopefully that kind of makes things clear with how we do this type of titration analysis. We're going to be doing more of these problems in the next chapter, where we actually calculate what the pH would be along these points as we add in various amounts of a strong base into a weak acid and vice versa.